Okay, great. So we stopped kind of in mid-sentence in the morning. We were working on a alternate construction of these topological defects related to ABJ anomalies. And as an intermediate step, we had shown that a theory with an ABJ anomaly had this interesting property. It was invariant under gauging a ZK one-form subgroup of its U1 magnetic global symmetry. So that was a feature that we had derived. And we're going to use this feature to construct this topological operator in a slightly different way. So in general, if you have a theory T invariant under discrete gauging, then it admits a duality, or perhaps you could call it a Dirichlet defect. So what's the picture? So what you do is you have the theory, and then here will be the defect. And this defect that I'm going to construct will turn out to be, in our context, the same as this d1 over k. So I'll just call it that. So here's the theory. And on one side, you have the theory, and the other side, you have the theory where you do this gauging. And now normally this is just an interface between two different theories. But now we invoke this sacred property, this self-duality. And so this is the theory again. So this, what we're doing here is we're going to gauge this one-form symmetry in half of space-time. And at the interface, we're going to find this defect again. Okay. So the explicit action so S is equal to S bulk, meaning whatever you have on the left and on the right, you just keep it. And then I'm going to put two terms. The first is the integral over x greater than 0. So this locus here will be x equals 0. These are the two sides. So remember our friends beta and gamma. So this term meant that beta was sourcing the magnetic one-form symmetry. This term turned beta into a ZK gauge field. And this term was our cleverly chosen discrete torsion. The difference now is that instead of gauging in all of space-time, so the whole region of X, which we decided was actually secretly the nothing operation, now here we do it in half. And I'm going to also add another term here. So the other term I'm going to add is 2 pi I over k integral over x equals 0 of star j plus, and you will see why I do this momentarily. So I add this combination as well. Now this, can anybody tell me what this is equal to? that combination? That's just 0, right? This is 0. This is trivial by my sacred equation, which was d star j is 1 over 8 pi squared f wedge f. So if I've chosen the signs correctly, that's just adding 0 to both sides. But it will be a convenient 0. So far from x equals 0, this is the nothing operation. We've gauged this zk one-form symmetry, which we know our theory is invariant under, and I also added 0 here. So, but something can happen at this interface. Okay? So let's note also, just to emphasize it, that beta and gamma are dynamical fields. And they are defined only now in this half space region where x is greater than or equal to 0. Now that's a region with a boundary, x greater than or equal to 0. So I need to tell you what happens to these fields at the boundary. Okay? So at x equals to 0, I will impose Dirichlet boundary conditions, meaning that I'll choose beta evaluated at x equals 0 to be 0. So this is some construction. I note that whatever this is, and we'll soon see it's the same as our original presentation of this chiral symmetry defect, but whatever this is, it's definitely topological. Why? Well, because the equation of motion for gamma makes beta flat, and so small motions, because of this Dirichlet boundary condition, small motions don't matter of this defect. So this is definitely topological. Now I want to show you that this defect is the same as what we had before. How will I do it? So the basic claim, which I will sketch out for you in a slightly cheating way, is that the edge modes of this beta gamma system realize U1 level K. So we'll see that by integrating out that this beta gamma system, we'll get our U1 level K, and that will then show that this duality defect is actually the same as our other construction of the chiral symmetry defect. So we'll have two different points of view. Okay? Now I'm going to go, again, kind of fast here. There's a whole paper essentially written about that. A very nice paper by Shao, Lam, and Seiberg. But if you want to see sort of fast, what you do is you look at the bulk equation of motion. For beta. So the beta equation of motion. We've been talking about the gamma equation of motion, but what about the beta equation of motion? So it says that d gamma plus beta equals 0. And previously we talked about how after eliminating gamma, treating gamma as a Lagrange multiplier, I see that beta becomes a zk two-form gauge field. But now we'll do it the other way around. We'll eliminate beta, and then gamma will come to life. So it will really be these edge modes of gamma that give rise to this Chern-Simons theory. Okay. So eliminate beta. And now what you get is minus ik over 4 pi. I'm not keeping track of the coupling to little f right now, but of course you can complete the square with that as well. That's not very hard, but let's just keep with this part. Ik integral over x greater than or equal to 0 d gamma wedge d gamma. That's just from the beta beta term and the beta gamma term, which is of course ik over 4 pi integral of gamma d gamma. So that's the U1 level K Chern-Simons theory in question. So what you are supposed to conclude from this reasoning is that this zk1 duality defect is the same as U1 over K of M3. You see that term there, that's star J. That's the U part, 1 over K. And then the F wedge F and the beta gamma system are giving this Chern-Simons theory together with the coupling of that Chern-Simons theory to the bulk. So we have essentially demonstrated this, which is of course what we called d1 over k at M3. Questions about that? Yeah.
Would other choices of boundary conditions say have given us like different stackings on the defect? Like,
if they're topological, then we can use this general theorem that says that you're always going to get something with zk1 form symmetry and prescribed anomaly times something decoupled.
okay, so I can apply this at the boundaries.
Yeah. Yep.
So when I gauge this zk1 form subgroup of U1 on the dual, this Z mod, this dual theory, do I get a dual Z1K?
Yes, but it combines back to make a U1 again.
Oh, I see.
Like you have an extension of U1 by ZK, which is again U1. It's just like it covers it K times.
Are we forced into this choice of discrete torsion, or like is it a free choice?
That was not a free choice. I needed that term was instrumental, for instance, when I proved that the theory was invariant under gauging the zk1 form symmetry, because that term was what produced this very specific shift in the theta angle, which I could cancel by the anomalous chiral rotation.
Otherwise, it's not going to be dual.
Yeah.
Mm. So is it the discrete torsion term that tells you that the U1 and the ZK combine back into the U1? Otherwise, like you have some other thing? Or if I gauge without the discrete torsion, do I still get?
If you gauge without the discrete torsion. Yeah, that's right. Yeah, that tells you that it's an extension. Yeah.
If you just gauge what ZK1 form symmetry in the Maxwell theory, right? You go back to the Maxwell theory.
Well, but I think it's the question of whether it goes to the magnetic part or whether it extends the... Like, you don't want to say that you get a new U1 magnetic symmetry and a ZK electric symmetry. Right? You want to have just a U1 magnetic one-form symmetry again.
I have a naive question. So on that board, why you can just insert recursive motion directly into the action?
This one, I'm cheating a little bit.
No, I mean the one on the very top. You just insert the star equation into the action.
That's not an equation of motion. That's the operator equation.
But I mean, operator equation means you can have contact terms, right? When you need other operators.
Well, that's the divergence of J is just equal to that expression, isn't it? I mean, let's see. You mean that there are about charged operators? Is that what you're worried about? Yes. Yeah. Let's see if I have
Charged operators inserted.
Well, I think, okay, maybe it's a little bit tricky. Maybe we should discuss it afterwards. It might take some more comments, but yeah. Okay, so, all right, it's nice to have two constructions. It's particularly nice to have this gauging construction for talking about the defect fusion algebra. So I'd like to spend some time discussing that. So of course, the punchline, which probably many of you saw coming, is that the price of this ABJ anomaly, well, there are various different things, but one thing we're going to see is that this operator is non-invertible. So it's topological, it commutes with the Hamiltonian, we can define it on any kind of spatial slice, but it's not a unitary operator. Okay? So let's investigate the fusion. Of d1 over k times d1 over k dagger. Okay, so what's the picture? Let's draw it first geometrically before we start associating equations. So we have our theory T. I'm going to use the perspective in terms of gauging. Here's our d1 over k. Here's T, where we gauge the ZK1 form symmetry. And here's the other duality defect, d1 over k dagger. And here's T again. It's the dagger because their orientations are reversed relative to each other. So here you have the theory T and the gauging on so left, right, and here right, left. So fusion just means we want to squish this together and see what comes out. It's topological, so nothing depends on this separation. Okay, now we can say what this is. This fusion. Well, it's given by what are we doing here? We're gauging this one-form symmetry on M3. Let's say these transverse slices are M3s, whatever that is, some 3 manifold, times an interval. So that's this region here, right? When we fuse this together, what we're getting is just this ZK. We have this theory coming for the ride, and we have this ZK1 form gauge theory living on M3 times an interval. And we know that there are Dirichlet boundary conditions at the ends of this interval. That's what we know. So basically, we need to learn how to compute this kind of partition function, a partition function of a discrete two-form gauge theory, ZK gauge theory, with Dirichlet boundary conditions. We need to know what the formula is for that. And we need to interpret it a little bit. Now, what are the gauge equivalence classes? ZK1 form gauge equivalence classes are in relative cohomology. So gauge equivalence class, I mean the gauge field modulo gauge transformation. So let me write a formula. So if I denote by the same symbol beta, the gauge equivalence class, then it's something where? It's in H upper 2, because it's a 2-form gauge field, so H upper 2. It lives in M3 times the interval. But it's a relative cohomology class, relative to the boundary. Why relative to the boundary? Because we're doing Dirichlet boundary conditions. So that means the gauge field is prescribed to be 0, to trivialize at the ends. And the way to take that into account mathematically is to demand that it's a relative cohomology class. Okay. ZK, of course, because that's the group that we're gauging. So if we had a manifold without boundary, we wouldn't have this relative part. But here we have boundary conditions, so it's just slightly more sophisticated. Now, fortunately for us, there is a version of Poincare duality that enables us to kind of manipulate that. So we'll apply what's called Lefschetz duality. This is Poincare for relative, basically. So it's the appropriate duality between homology and cohomology when you have relative cohomology. So what does that say? It says that this group, H upper 2 of M cross I relative to the boundary of M cross I with coefficients in ZK is isomorphic to H lower 2 of M cross I with coefficients in ZK, where I get to forget the relative part. And then there's an easier step, which is that now, since I'm in regular cohomology, I can just shrink this interval. There aren't any interesting 2 cycles coming from that interval. So this is just H2 of M3 with coefficients in ZK. This is not very surprising. You could have guessed this. What is it telling you? This non-trivial gauge field, how can it be characterized? Well, it's a flat gauge field. We're doing ZK gauge theory, so there isn't any curvature. All there is the appropriate generalization of holonomy, in this case, Wilson surfaces. Okay? So it's characterized by a surface S where it has holonomy. It can be even more specific. So if we use the equation of motion, which relates beta and F, we can look at a Wilson surface of beta. That's a surface in M3. Could be in the middle of the diagram, not necessarily at the endpoints where it vanishes. This is the same as 2 pi I over k integral over S of F over 2 pi. And what are these? These are the ZK1 symmetry generators. Right, so we have the magnetic one-form symmetry. And we have this ZK1 one-form symmetry that we're gauging. And the point is that this sum over Wilson surfaces that's sampling this ZK, that's creating this ZK one-form gauge theory, we can view it equivalently as a sum over these symmetry defects. And so that will give us a nice formula. Yes?
The beta vanishes at the boundary,
Yeah. So it's in the, think of it as in the middle.
but then can't you move it to the boundary? Or is there some discontinuity?
I'm being a little bit sloppy about where I'm like imposing this equation, basically. Let's see. Let's see, if we solve the equation, you will get beta is 1 over k times f. No, I must be... Well, I think your question could have been asked before, right? You're asking, like, not really about this equation. You're asking about this formula for the Wilson surface. Why is this not just trivial, right? No, but it's true that in the it's definitely true that in the bulk region, the Wilson surfaces are not trivial. And there probably is some tricky part about the cohomology versus homology. Okay. Maybe we also have to ask this one in the break because it will probably take me a while to disentangle when I use this equation of motion precisely. But the point is that, the point is that the one-form symmetry defects do not vanish. And so after I gauge the ZK one-form symmetry, you can ask how is it possible that the theory is self-dual? Okay, don't I reduce the one-form symmetry? And you get new one-form symmetries, which are the Wilson surfaces of beta. So those are sort of, you do the quotient, but you gain them back through the Wilson surfaces of beta. And all I'm trying to say here is identify those Wilson surfaces with the kind of original presentation of the symmetry, right? Like under this self-duality map. Okay. Okay, so thanks for all the questions. So the partition function of ZK one-form gauge theory is a sum over these betas. So that's what's going to give us the fusion rule. That's what we needed to do. We needed to compute the partition function of this ZK one-form symmetry gauge theory on this interval. So there's a sum over S in H2 of M3 with coefficients in ZK. Here, the defects here are supported on M3, so there's a 3-manifold in the problem from the outset. And here we put these surface integrals of the one-form symmetry. And then there's a number here, x. So x is a coefficient that I haven't fixed yet. But this part of the formula we have essentially derived. That this is the partition function of the one-form symmetry gauge theory. It's a sum over Wilson surfaces. And we can identify those Wilson surfaces with the generators of the magnetic one-form symmetry. Okay, so there's a constant x here in the problem. Let's compute x. Okay, so x, what is that? Well, it's the standard normalization for ZK one-form gauge theory. What does that mean? It's a ratio of various cohomology groups needed to divide out gauge transformations and gauge transformations of gauge transformations, etc. This kind of standard factor. So in this case, what will it be? It's H0 of m times I the order of that group divided by the order of the one-dimensional cohomology. Again, where does this come from? When you do gauge theory, you should divide out by the gauge transformations, the kind of residual gauge transformations. That's this H1, where you have two-form gauge theory, so the gauge parameter is one form. But then there are some redundancies in the way of parameterizing the gauge parameters, and that gives you the H0. So you can evaluate that formula in general. It doesn't depend on m. That's a nice feature. It's just a number 1 over k. Okay, so I have, with some squinting, sketched out for you the fusion algebra. D times D dagger is not 1, but it's that mess on the right-hand side. And I'd now like to give you some comments about that mess on the right-hand side so you can get some feeling about it. Okay. So, interpretation of the fusion. Yeah.
Have you used an Euler counter term to make it 1 over k?
Have I used an Euler counter term to make it 1 over k? No, because this this defect is on a 3 manifold, and so the Euler characteristic is just 0. Okay, so how should you think about this? The right-hand side of the fusion up there is what's called a condensation. Unpacking that technical term, condensation, would take us a while, but what you can think about it is that we started our life talking about gauging the ZK one-form symmetry in all of space, in all of space-time, in half of space-time. What's appearing there is something different. We're gauging the one-form symmetry only on M3. We're summing over some kind of symmetry defect, some insertions of the one-form symmetry, but only on M3. So instead of modifying the theory, usually you think gauging in all of space-time modifies the theory, this creates an operator in the theory. Okay? So it's some kind of operator. Now, what can you say about this operator in general? when acting on local operators, what happens? Well, no local operators are charged under one-form symmetry. I began with that basic piece of information yesterday. So when acting on local operators, the right-hand side is completely trivial. Right? So zk1 doesn't act. So this means only s equals 0 is relevant. And then we get d1 over k times d1 over k dagger equals 1. Did I get 1? 1 over k. Thank you. 1 over k. Yeah. So not 1, but definitely invertible. So on local operators, you don't see anything super unusual except for that normalization. How can you see the non-invertibility? Where do you have to act to see that?
Just to make sure, the operator on the right-hand side is also a topological operator.
That's correct, yes. Because f is the integral of f over a surface is a topological operator. It is the codimension 2 operator that generates the one-form symmetry. So that's a sum over the codimension 2 operators that generate the zk one-form symmetry. So it's a kind of funny topological operator. You know, this formula, you think you have this d, which looks like it's codimension 1, and you're fusing it with d dagger, and you're supposed to get something codimension 1, right? It's supposed to, and you do, but it's some kind of it's an imposter. It's a codimension 2 defect that's trying hard to appear as codimension 1. It's a sum over these codimension 2 defects all along this locus M3. And you can think kind of geometrically that that's why local operators don't see the right-hand side in an interesting way, because the right-hand side is like a mesh of these surfaces, so it's porous. Point operators can fly through it. Yeah?
Sorry, in this derivation, what's the destiny of the discrete torsion term? I mean, because...
Yeah, good, thank you. In the derivation of the fusion algebra with d and d dagger, the discrete torsion term doesn't enter in any interesting way. However, if you consider the fusion of d with d, then the discrete torsion term will hit you in the face. So it's specifically this d with d dagger one that has this very universal, always sum like that condensation. But the other ones will be very sensitive to the discrete torsion. So yeah, so that's a general feature. So these duality defects constructed by half gauging, they always have this d dagger is sum over is a condensation form, but their dd and other kinds of fusions are non-universal. Yeah.
Is there something that tells us that the inverse has to be dagger? Like, couldn't there be like some weird operator that could invert it?
Well, the reason I'm going to compute dd dagger is because if I find that dd dagger has a bunch of 0 eigenvalues, then d is definitely non-invertible, which is what I'm going to do right now. Yeah.
Do you assume that M3 is connected there?
Yeah.
If it is not, you have like some power of connection.
You'll have some factors, yeah.
Is there a simple way to see that the defect is simple?
To see that it is simple. There probably is, but I don't have a snappy answer. Let's see. Let me brood on it a little bit. I'm sure there is a good answer to that, but it's not coming to me right now. Yeah.
Think about it in terms of the Chern-Simons formulation with level k. So now we have something with level k and level minus k, right? That's like this dk dagger.
Yeah.
So somehow
I'm telling you that just gives you this like zk one form gauge theory. Yeah. Partition function. You can also.
But zk one form gauge theory is same as zk zero form. It's usual zk one form, not.
Yeah. It will be a usual gauge theory with a. It will be like a usual gauge theory with a torsion term.
Oh, with a torsion.
Yeah.
But just let's say f equals 0, right? That partition function seems like it always gives me something positive.
Yes.
It's not like, I don't know, 2 minus 2 on RP3 has a 0 partition function.
Well, I think I've derived the fusion rule correctly, but you're asking me to identify which zk gauge theory it is.
Maybe I'm barking out the wrong tree. We can talk.
No, there is some duality like that I mean, because when you try to compute the fusion using the original presentation, you'll end up with the two Chern-Simons theories, and you want to compute their partition function and show that it's the same. So that can be done. Yeah, that can be done. But what I'm not remembering is that identifies it with which particular, like there's a more familiar description of that product Chern-Simons theory, and that's what I'm not remembering. Okay, so the last thing I wanted to say about this fusion rule is, okay, so I wanted to show you that this is really non-invertible, that it's not just an accident that dagger isn't the inverse. So the right-hand side can be 0. When can it be 0? It's on states with magnetic charge. Okay, so, right, we shouldn't be surprised that this is where we need to go to find something interesting, right? To really sort of activate the ABJ anomaly, we thought we needed 2 cycles or magnetic charge. So what to do? So let's consider, for example, space is S2 times S1, and I'm going to eventually act with D on this Hilbert space. So the Hilbert space decomposes. So we look at the Hilbert space on S2 times S1. It's a direct sum over integers m of these sectors that I'll call HM. And what is HM? So on HM, the integral of f over 2 pi on this S2 is equal to m. So these are the sectors carrying definite magnetic charge. So now let's act with that fusion rule. So on HM, what do we have? D1 over k times D1 over k dagger is 1 over k. Sum. So there's only one 2 cycle here, right? Where M3 is S2 times S1. There's only the 1 2 cycle. So that sum over 2 cycles is just a sum from I equals 0 to k minus 1. Well, maybe not I. L equals 0 to k minus 1 of a phase 2 pi I L m from the magnetic charge over k. And I think we can hopefully evaluate this. This is 1 if k divides m, and 0 otherwise. So this should put to bed any question about whether this operator has an inverse in general, because d times d dagger has this huge kernel. So d includes this projection.
If it had an inverse, right, and the inverse wasn't the couldn't we always choose for unitary theory? Couldn't we always choose to represent the action on the theory such that the inverse is the adjoint? Isn't that?
Well, for a unit, I mean, is your question whether all invertible operators are unitary? That's not true.
No. But if they're group-like operators, we should be able to represent them as unitary operators. Right. So it's we should always be able to make a choice so that it's.
Well, I'm not sure what we're choosing, but anyway, this operator is definitely not unitary or invertible. Okay, questions about that? Yep.
For the overall normalization, the fact that it's not an integer in the sum, this is okay because it's not a simple defect we're looking at?
No, I think this is a simple defect. Sorry, who's...
No, sorry, in the sum. Like, it feels weird multiplying a defect by not an integer. But this is not an individual term. Yeah, the right-hand side, I think, is simple.
So what does a simple do?
I just meant like the sum. This is the sum of the things.
Okay, but let's answer Slava's question because it will make the discussion more clear. In QFT, okay, so when we just talk about operators acting on Hilbert space, it makes sense to add them, to subtract them, add them with general coefficients. Right? We think about them as linear over the real numbers or complex numbers even. Now, when we think about defects, this is no longer the case, right? If I want so by defect I mean think of the object as being extended in time. Okay, so now it must define a consistent Hilbert space, and there's no sense in which you can multiply a Hilbert space by a complex number and get a well-defined Hilbert space. Okay, so if we think about Euclidean invariant QFTs where we want to be able to convert between operators and defects, then they're no longer, these things that we're thinking about are no longer linear over complex numbers. It at most makes sense to take positive sums of them because there is a direct sum notion in Hilbert space. And so a simple defect is a defect which is not the direct sum of two other well-defined defects. So it's kind of like a minimal unit. Okay. Yeah.
Is this sum? This is not a direct sum, right? This is a sum, or
what's this?
The fusion of D and D.
That's a sum. That's not a direct. That's just an operator that can act.
For the 1 over k, well, if you put the D on a sphere, you can fix it, right?
Yeah, but it costs you the factor. Right? You could think that like the quantum dimension of this thing is not 1. Right? If you wanted to define a higher dimensional version of quantum dimension by saying what's the expectation value of D on a 3-sphere as opposed to just on a circle, which is what you would say in 2D, then its quantum dimension has this square root of k in it, 1 over square root of k. More questions? Okay. Then we've constructed this beast. We've seen its fusion rules. Let's talk about its action on various operators. Let's derive selection rules. It's a symmetry. And we want to be able to use it to do something. Okay, so the first thing is local operators. Well, local operators are blind to this TQFT. That was all about coupling to the one-form symmetry. So they see only this U1 over K. So in other words, D1 over K, when I think of it as acting on a local operator O, it just transforms it by the expected phase. This works for any K. So we get the full chiral symmetry selection rules. Now, you might say that's a little bit disappointing. Wouldn't it have been great to derive something new? But actually, this is a hint that we were on the right track, because actually we were trying to find a topological operator which could do this, could give us the expected selection rules on local operators, was well defined in general, and it's allowed to do something more sophisticated when we start talking about extended operators, and that's what we're going to see now. So now let's talk about the action on tuft lines. This will be more interesting. So let me give some notation. M of L, this will be our tuft line. On L, we've seen this a number of times. So, here's our line L. Here's the linking two sphere. And the integral of F is equal to M, which is the magnetic charge. We'll mostly be interested in the case little m is 1, but I'll keep it general for now. So we want to figure out, how does this operator, this duality defect, or this non-invertible chiral symmetry, how does it act on the tuft line? Okay. And we need the effect of the theta angle. So I'll review that briefly now. We need to know the effect of a theta angle in gauge theory on electric and magnetic charges. This is the so-called Witten effect. So I'll assume that you haven't seen it, and I'll quickly just sketch something out for you. So we're interested in a line L such that there's our gauge field F has that property. So when we consider the variable in the path integral, we have that F is equal to some F monopole plus dc fluctuating. So there's some fluctuating shift that's regular, that's not allowed to correct the monopole charge. So considering correlation functions of the tuft line, you're supposed to insert this kind of expansion. So this is the dynamical part. Okay, so now let's impose that the action S contains a theta term. So it contains I theta over 8 pi squared integral f wedge f. So now we just take this thing and we plug this formula in here. So F monopole plus DC fluctuating. F monopole DC fluctuating. Now I'd like to keep track of only the cross term here. So I want to keep track of the term where the fluctuating gauge field hits the background part. So what does that look like? It looks like I theta over 2 pi. I'll say contains. Then we've got the integral of F monopole over this 2 sphere. And then we'll have the integral of this fluctuating part, where are we integrating that, over the transverse space. Right? We want to make up the 4-dimensional space-time. We've got these 2 angular directions. So we need to integrate along L. And we also need R greater than or equal to 0. So R is like the radial direction off the monopole. Okay. This we know. We put that in. That was our signal that we're considering the magnetic charge. That's our M. And this we integrate by parts. So this gives us I theta M over 2 pi integral along L of this fluctuating part. What do we conclude from this? This is the coupling of the gauge field to electric charge. Right? An electrically charged particle couples by the Wilson line of the fluctuating gauge field. And here you see it. We thought we were starting with something purely magnetic, but because of the theta term, there's a term that looks electric. That's the Witten effect. So the theta term induces an electric charge which is m theta over 2 pi. Now, this was a little lemma for us. We needed it to derive how the defect acts on 't Hooft lines. And the essential point was that we saw that effectively across this d1 over k, the theta term jumps. So if we start with m, it will get an electric charge (1 over k). We could try to write it more like a formula. d1 over k acting on, say, the minimally magnetically charged line, m, gives us m on the same line, L, and then something that we'd like to call the Wilson line to the 1 over kth power. Now we need some comments about that. But to start, you could think this is an improperly quantized dion. It's improperly quantized because it doesn't seem to have integer electric charge. Now, let's say in a more transparent language what an improperly quantized dion is really supposed to mean. So this improper quantization implies that it's not a strict line. what do I mean? Well, w of 1 over k, w to the 1 over k, this kind of fractional charge, you would like it to be the Wilson line of C with a charge 1 over k. You would like this. Now that doesn't make sense, as it doesn't depend just on the line. But what you can write is the following, where sigma is a surface whose boundary is L. This is an open surface operator. Okay, it's not too bad of a surface operator. What I mean by that is that its dependence on the surface is very mild. Its dependence on the surface is topological. Why? Well, again, we recognize that this is the one-form symmetry generator. Right? That integral of f, that's the surface operator generating the magnetic symmetry. If it was on a closed sigma. Here we've tried to cut it open. The boundary is not topological. But the bulk wiggles of sigma are topological. So we can draw a picture.
Where did sigma come from? So it was not attached to.
Yeah, I'll draw it. Maybe let me draw the picture, and then it'll become clear. Yeah. So good question. Where is sigma? So here's this d 1 over k. And here, we need some colors for this. Here is this magnetic monopole world line. Now I try to cross them. That's what acting is supposed to mean. So again, I have here d1 over k. Here again, this m. And there are various choices, but one choice is this one. So there's the sigma. Can end here. It could also close up. There are choices, but this is maybe the cleanest one to think about. So this sigma here, this is the topological surface operator. Now, this is a weird picture, especially if you've never seen non-invertible symmetry before, but I'd like to advertise a general feature. A feature of non-invertible symmetry is that it can change the type of operator. So standard invertible symmetries, they map points to points, lines to lines, surfaces to surfaces, etc. Here we see some kind of funny mixing. left-hand side started as a genuine line, no surface in sight. Right-hand side, when it gets acted on by the symmetry, we have this topological surface. Okay, so in our case, we had this line being exchanged with an open topological surface. And there is a direct analogy to the order disorder map in the Kramers-Wanier duality. Which is another kind of example in lower dimensions. So here what we have is some kind of higher version of that. Points are still going to points, but lines are going to open surfaces.
So this picture is reminiscent of Hanani-Witten, but in that case,
it's reminiscent of what?
It's a Hanani-Witten transition, right?
Yes. Yeah.
In that context, the sigma, the choice of sigma was a physical object. It was some extra string stretching, for example. Whereas in this picture, sigma is a kind of arbitrary choice.
Well, the dependence on sigma is extremely weak in this picture.
Okay.
Right. So different sigmas will give you different answers, or give you the same answer. Same
right.
answer, right? Yeah.
Right. So in a sense, it's not a well, I don't know what I mean by physical, but it's not like there's some physical object is sitting here.
Well, there's a topological object sitting there, right? I mean, this surface is not a trivial operator. It's just a topological operator.
Yeah. Okay.
Like think about maybe a case that I'm sure you'll hear about in the next week in the school is, if you have correlation functions with branch cuts in 2D conformal field theory. Are the branch cuts physical or non-physical? Well, the location of them is rather arbitrary, right? Those are topological lines. But you could still detect the fact that there is a branch cut somewhere.
Okay. So you mean something about the upstream, position of the upstream.
Yeah, but it's noticeable, right? Because it's because it's an improperly quantized charge. The sigma, the fact that there is a surface is measurable here. Was there another question? Yeah.
What is the way that the surface intersects the defect? Like, what is the information there?
Just a one cycle. This sigma can have a topological boundary there. There's another choice of sigma, which I also could have drawn, where it doesn't end there, but it just fills in this disk. That's also possible. Yeah.
If the one-point symmetry participates in two groups with another one-point symmetry, then this kind of operator is also ruled out.
It's what?
Or it's just because the target operator of the.
I mean, you can combine the first day with the second day to get very sophisticated algebraic structures, higher groups involving non-invertible symmetries. People have tried to do that, but I'm not doing it here. Yeah. Nothing else? Okay. Okay. Let's do some selection rules. How do you derive selection rules in correlators? Well, maybe I'll skip the derivation of the selection rules on local operators. It should be unsurprising that you're going to get the same thing as you would have expected, because the local operators are just blind to the TQFT. So let's do a selection rule involving line defect, if we can. Okay, so here will be a 4-sphere. And let's see, here is a local operator, O. There can be many other local operators. Let's see, M was in red. And here is M. Okay. Now what do? You want to derive a selection rule. So you're supposed to grow a small bubble of the symmetry defect. Okay. again red, here, and then maybe here will be, this will be our dk, d1 over k, excuse me. And the cost of growing a small bubble is not 1, because d evaluated on the 3 sphere gives us a factor, this 1 over root k. So these are only equal if I multiply them by 1 over root k. This is on the 3 sphere. Okay. Now I grow this thing. I try to pass it through the other operators and shrink it on the other side. Okay. So it has to pass through the local operators. That's easy. That gives us a phase. Here I've just got one operator, so I'll keep the phase. Just one phase there. And then I also have this open surface operator. And so the disk gets filled in. And now, if I want, at the very end, I can contract this d. Contracting it, again, costs me the 1 over root k, so I get rid of that now. And I'm left with this picture here. So this is a selection rule. The equality of this and this correlation function. This is a new result. So correlation functions of local operators obeying the chiral symmetry selection rules. This is known for a long time in various guises. But here you see that once you start looking at correlation functions involving 't Hooft lines, the chiral charge is not conserved. Q can be non-zero. Here, the net chiral charge is not conserved. Instead, you just get a relationship between this one, where you have a genuine line, a 't Hooft line, and this one, where you have this improperly quantized dion. You just have those correlators have to be equal. Yep.
Is there any subtlety in shrinking it because it is attached to the magnetic line after you pass through?
Well, that's why I chose this other surface. Which surface you choose doesn't matter because of the topological nature. You can show that more formally, but yeah. You can also, if you have 2 of them, there could be a choice where you have a tube connecting them. There are different choices.
Sorry, but is it actually a selection rule in the sense? I mean, we get a relation between two correlations.
Because it's not a 0? That sounds like splitting hairs to me. It's an equation between correlators. Yes. Non-trivial equation between correlators. If you like, you can move this over here and say that the difference between them is 0.
It doesn't give a criterion to say if a correlation function is 0 or not.
That's right. It gives you something different, which is that this is equal to this.
Well, it does, because we can define our new operator, which is a linear combination of M and this topological open top of the topological surface. And then, in terms of that operator, we'll have stuff.
Yeah.
So does anything interesting happen if you change the S4 into S1 times S3 and having everything stretching along this?
Yeah, so great question. So for instance, Max asked me at the beginning, when I was giving this motivation from 't Hooft, like, you know, that 't Hooft reasoning is only valid for S4 if you choose T4 or maybe some other manifold, S1 times S3, everything looks different. And the utility of having the actual construction of a topological operator is it gives you a way to address all those questions at once. You just do this same manipulation. You try to grow it and move it across and shrink it. You might get stuck on the topology of the ambient space, but then you try to manipulate that too. So yeah, so you can address all of those questions simultaneously. Yeah.
So as a space-time picture, this loop is like I create.
This is in S4. I don't know where. I mean.
But if I like pick a time direction, this M is like monopole, anti-monopole, and then I pull it back.
Sure. If you want to think of a Wilson line as a quark, anti-quark, and then you put it back, yeah.
And so if what's the surface mean, sort of, when I do this? Or?
Well, you could say that it's a dion, anti-dion.
Oh, but it's not quantized.
But it's just a wrong quantization, yeah. Yeah.
Would it be possible for us to start from already a dion on the left-hand side and get an actual selection rule?
You mean, again, about this question about whether it's 0 or just equal to something else?
Yeah, I mean, like, maybe we can start on the left.
I mean, you can act, you can, using the rules that are on the board, you can act on that on any line defect and get various other line defects. Yeah. Yeah.
If I complete this, is there any notion of this where I can understand where this topological surface comes from? Like, I can understand where monopoles, for example, come from, right? Can I get any understanding of this W over K or not?
Is your question about, not sure I exactly understand. Is your question about if the monopoles become dynamical, what happens?
Yeah, my question is kind of, I can understand the tuft lines come from the heavy broke monopoles, but I was just wondering if there's any UV realization I can get.
I see. No, but I mean, UV gauge theories can have surface operators too. Okay. So maybe they're just less familiar. Yeah. Yeah. Okay. All right. So we have like 15 minutes roughly. So I will spend the rest of the time talking a little bit to you about non-invertible symmetry breaking. I began these lectures by saying if you have a symmetry and you want to apply it to particle physics, you should think about its mechanisms of breaking. And here we've spent a long time going through the details of this non-invertible symmetry. So let's think about non-invertible symmetry breaking. What can you expect? Let's see how much. Okay, this is perfect. 15 minutes. All right. So let's go back to our kind of money equation for the fusion. D 1 over K times D 1 over K dagger is this sum. Like that, omitting some of the details. So we want to consider this algebra, and we want to consider an RG flow where we have a UV with this defect broken, the symmetry broken somehow, and an IR where D emerges. And we'd like to understand what can we say about such a situation. And there will appear a kind of novel symmetry breaking possibility. Okay. Okay. So dynamical monopoles we know that they can break the magnetic one-form symmetry. And we also see that the chiral symmetry is in some kind of funny algebra with the one-form symmetry. Okay? That's what you should take away from this formula. Somehow, we managed to produce a non-trivial algebra between the chiral symmetry and the one-form symmetry. Okay? So if I have dynamical monopoles and they break this one-form symmetry, this formula tells me that's going to be communicated over here and somehow break this symmetry. So this implies a breaking of this chiral symmetry. Now, we could try to estimate that, try to understand what would be the characteristic scales involved in that sort of mechanism. So let's estimate it. How will we do it? We're going to do it in the infrared. Right? We want to kind of have a universal estimate. We'll estimate it by coupling to the monopole world line. So, you know, it's hard to couple monopoles directly to U1 gauge theory with charged electric matter. But there is one way to do it in the approximation where the monopole is treated as heavy. The monopole runs in a loop. Look at the first quantized picture of the monopole. And that can give us an estimate here. So what will we need to know? Just going to be very crude here. The monopole mass let's estimate that as lambda over g. You could think here that lambda is something like the Higgsing scale. Imagine I'm going to eventually embed my U1 gauge theory in a non-abelian theory. So then there's a Higgsing scale coming from that. And g would be the coupling. So there's typically some pi's and stuff there, but that's the formula. The other thing I would need to know is the cutoff, the IR cutoff. Okay. Well, again, thinking maybe about a UV completion as a non-abelian gauge theory, the IR cutoff, what would it be? It would be something as lambda times g. Right? That's like the W boson mass. Right, those are typically the lightest particles, at least when g is we're thinking of g as small. Okay? Now this cutoff, you could think that it creates a shortest distance or time scale that you're allowed to study in this IR effective field theory. Okay, so what's the first correction? Sorry, UV cutoff, yeah, UV cutoff. It's a cutoff of the IR effective field theory, the UV cutoff of the IR effective field theory. Thank you. The first correction due to a loop of monopoles. So again, my favorite squiggly loop. But now I think of this as a finite mass particle. This should go like exponential of minus s of this world line loop. First correction, sorry, to the infrared effective action. So imagine I have my U1 gauge theory, and it now couples to a dynamical monopole. And I want to understand what's the size, typical size of an operator that having a loop of a dynamical monopole would generate. This is what we want to do because the loops of magnetic monopoles are the first effect that will break the one-form symmetry here. Okay. So I'm just going to estimate this in a kind of non-relativistic way. We're thinking of the monopole as very massive. So we have mass of the monopole, the rest energy, and then for a small loop, the shortest time it can go. The scale cancels. and you get some pure numbers, which we definitely can't keep track of from this kind of reasoning, divided by g squared. So what do we expect this? We expect that a loop of monopoles will kind of the first correction when you have dynamical magnetic matter to generate a non-perturbative violation of the chiral symmetry.
I'm having a hard time following this argument because this is just a constant, so it's just some constant term in the actual partition function that you exhibited. Constant doesn't violate any symmetry.
Yeah. So good. So very good. If you want this to be an operator as opposed to a number, then I'll have to be more careful. So how would it be an operator? For instance, suppose the monopole has some fermion zero modes, right? Then this would multiply the product of those zero modes. I'll show you that actually momentarily. Yeah, but I'd like to give this intuition just so you see the size. Now, this sounds a little bit slippery. What's a more pedestrian viewpoint? Where would those non-perturbative violations naturally come from? Well, actually something very familiar. Okay. So the monopole arises in non-abelian gauge theory. So in the IR, we have the equation we've been studying all day. D star j is 1 over 8 pi squared f wedge f, and that led to this non-invertible chiral symmetry. But I can just upgrade this in the UV to d star j is 1 over 8 pi squared trace f wedge f, where this is now a non-abelian field. Okay. And we've discussed several times that in non-abelian gauge theory, the chiral symmetry is violated directly by the instantons. Okay. And indeed, you can say, well, the size of this effect is up to those numbers that I didn't compute for you, the right kind of qualitative formula to be an instanton action. So perhaps the right way to proceed, if you want a concrete formula, give me 5 minutes, say, is to consider the effect of instantons. Okay, so let me give you just an example. Let's do an example with an exponentially small mass. Okay. So my UV is SU2 gauge theory plus 2 doublets chi I and phi an adjoint scalar. No one-form symmetry. Okay. The RG is that this condenses. So and what will the IR be? The important part will be a U1 gauge theory and 2 Dirac fermions. So I here equals 1 and 2, labeling the species in the UV. And this IR theory has this non-invertible chiral symmetry. So this UV has dynamical this RG flow has dynamical monopoles, and you expect these exponentially small corrections violating the chiral symmetry. You can see it directly, calculate it, using the instanton of the UV. So these should be viewed as 2 different points of view on the same physical effect. A loop of monopoles is the infrared way of describing things, and instanton is the UV way of describing things. So, the one instanton. So let's look at it supports 1 fermion 0 mode for each doublet. So it's for this reason that it generates an operator, because it supports 0 modes. This is the so-called 't Hooft vertex.
Sorry. Maybe I missed something. Why do you mention there's no one-hole symmetry there? The doublet is in the joint, right?
No, doublets are the fundamental.
Oh, but you say the joint there.
Phi is in the adjoint. Phi is in the adjoint. The fermions are in the doublet. Fundamental, yeah. Okay, so there's 1 0 mode for each doublet. And this tells us that the instanton generates a fermion operator, a multi-fermion operator, which saturates the 0 modes. So LUV will get a correction that looks like this. This is the instanton action. This is the multifermion operator, 1 for each 0 mode, sometimes called the 't Hooft vertex. We can write it in terms of the infrared. Again, same factor. And now I expand it out. It's chi1 plus chi2 minus the opposite term, like that. And so this is, as advertised, an exponentially small correction violating the chiral symmetry. So this is a technically natural exponentially small correction. And so that's sort of an interesting starting point for applications of non-invertible chiral symmetry to model building, to phenomenology. You see that one of the natural symmetry breaking mechanisms generates exponentials. That's nice, especially if you like trying to explain small numbers in nature. And so people have tried to write down models making use of this kind of general mechanism. Okay, so I'm over time already, so I'll stop here.
So in this case, V doesn't really emerge because it's
because of that term.
Yeah, so it doesn't go away. I mean, it's just a feature.
Yeah, it's a feature, yeah. I guess what I would say, the right thing to say is that it's a kind of technically natural small correction. Yeah, Max.
In the infrared theory, it's supposed to take the loop to be a bit bigger so that you're not working at the cutoff scale exactly. Could you understand this math generation already in the infrared theory?
Yeah, so great question. So I didn't say much about, I kind of suggested, but did not say why. There is a match between monopole loops and instantons. And this is something that has been worked out for some cases, but not for all cases. So for instance, people have shown that, instead of doing QED, I could have done axions. People have shown that you can generate an exponentially suppressed axion potential from a loop of monopoles, like how to do that directly in the infrared theory. Now, to do it for the 't Hooft vertex, people have not yet shown. It seems likely that it will work because the monopole also supports the zero modes. And so you want the loop of monopole, you want to like write the 't Hooft vertex in that way. But nobody did it directly yet.
Do we understand the boundary condition for the monopole, like how the massless fermion scatters on the monopole?
We do know, yeah, so in the last couple of years there was some kind of significant progress on that thanks to these kind of ideas, yeah.
So I have a question. So the point, one of the points here is that there is a UV description, IR description, and then you can try to do it in IR.
Yeah.
But in the sense, once you want to evaluate it in a precise, etc., it seems that you need a UV completion anyway, no?
I think that's kind of what Max was asking me, was like, if I know just that the monopole, did I have a monopole, dynamical monopole, does that give me a way to evaluate the answer already? And I think work is ongoing on that. So for instance, it is known how much a loop of monopoles corrects the axion potential without saying anything words about UV completion.
I see. So you suspect that, but for example, the precise coefficient, etc., shouldn't that depend on the UV completion? No? There's a coefficient there. See?
This number here? Yeah, for example. I think it depends on very little about the UV completion. Yeah, it depends, you know, like for instance, it depends on the difference between the monopole mass and the dion mass. That kind of thing. But just that.
I see. So it's not completely UV independent maybe, but probably you can
a
little bit of extra assumption about it.
Yeah, you don't need to say pick a UV gauge group or a very specific UV completion. Yeah.
I don't know, like, you know, ideally you probably want to kind of shrink this loop as much as you can, and then you're kind of working at the cutoff scale, so then it's not clear that this is really a monopole. That this, you know, the monopole loop dissolves into an instanton there, right? So it's clear that just knowing the mass of the monopole.
Well, we should talk about it more, but the example that I know where you can compute the axion potential, that's done in a really nice paper by Matt Rees and Gigi Fan. That example, they needed to know very little information. And they kind of tried to parameterize how sensitive they were to UV corrections. This seems pretty reasonable. Yeah, we could talk about more. Yeah.
This is an actual phenomenological question, but should this effect be any stronger than, let's say, baryon number violation by the weak interaction? Or?
baryon number of, should it be any strong?
Like also just some incident calculation.
Well, right now this is some instanton calculation. That's right. Yeah. Yep.
So is there like a corresponding emergence theorem in the first lecture here where I guess U1 magnetic has to survive before this D?
Yeah. In a sense, I was using a version of that to say how to that if you break the one-form symmetry, you necessarily break the chiral symmetry.
Okay, shall we go for a break and then please, if you have questions, please ask him in the middle, please.